Alright friends, welcome back. In this video I'd like to go ahead and take a look at a second day for our P.2 section in our textbooks. This is in the prerequisites chapter, and this one is going to talk all about radicals. Okay, so we're going to talk about what radicals are, we're going to talk about how to punch them into our calculator, and then we're going to talk about how to simplify radicals, which is probably the more important idea that we want to take away from this video. So real quick to start off, just a quick definition here. Every single radical that you will at is going to have an index and it's going to have a radicand. Okay, so the index is telling us what kind of root we're taking, and that's going to be this number. That's that little superscript number outside of the root. We call that the index. And then of course that number that is underneath the root, we call that the radicand of your expression. Okay, so it's a little fancy word that basically just means the part that's underneath the square root symbol. All right. Anytime you guys have a radical, that is going to be the two basic components of it that we want to pay attention to. And just taking a look at your calculator, in order to go ahead and punch these into the calculator, there's a couple of buttons that you can press to go ahead and pull up some various different roots here. So let's say you just simply wanted a square root. All you're going to have to do is press second and then the x squared button. Your second button up here in the top left-hand corner. And my pen just did something very weird there. That's odd. Let me switch back to my stroke eraser there. So the second button is right there, followed by the x squared button, which is right there. That will allow you to pull up a square root. You could even see that little square root symbol in the corner of the button. In general, what that means is the color that that little symbol was printed in is going to tell you what button to press first before you press this x squared button in order to get access to that function in there. Okay, so second x squared will pull up a square root. If you wanted to pull up a cube root, then that would simply just be your math button and then the number 4 button. Okay, so the math button is sitting right here underneath the alpha button on your calculator, and that will allow you to pull up a cube root just like I did here in this line of this work. I did the cube root of 27, but let's say you wanted to do the root with any index you want. Well, that's going to be this last case here. This is an nth root, so if you press the math button, again that's right here, and then followed by the number 5 button, you're going to be able to pull up a radical with any index you like. So here I did the 5th root of this big number here, and that turns out to be 8. So again, just a real quick about how to punch these into the TI-84 calculator. If you don't have this type of calculator and you're curious about how to go ahead and punch that into one of your own, then just come see me and we can figure it out together. Okay? Real quick on this right here, again, just kind of taking a look at how to evaluate. This would just simply be 2 if you were to punch it in. So we'll go ahead and just point that out as our first little result there. This is just a practice using the calculator type of example. So right here, these are all the different properties of radicals. I don't want to get us too bogged down on explaining each one of these properties in depth, but I do want to kind of point out some things about them, okay? So this first property basically talks about the order with which you do these operations, because if you look on the left-hand side, they take the a to the mth power first, and then after that, they apply the nth root. And what this property is saying is that that is exactly the same as reversing the order of those two operations. Maybe instead, on that number a, you take the nth root first, okay, and then follow that up with taking the exponent of n. So that property is going to say that those are basically the exact same process. You can reverse the order of those operations, and you still end up with the same equality. The next 3 rules talk about how to condense. Okay, they talk about how to condense into a single root. Okay, so whether you are multiplying or dividing, or you take the root of a root, in the case where you're multiplying or dividing, the only thing that you're going to have to really pay attention to is the fact that your two roots need to have the same index before you can condense it down into a single root with that index, okay? And then that very last one just says if you take the root of a root, you could just make it a new root where the index becomes the product of your two indices that came before, okay? But it's property number 5 that I want to spend the majority of our time on here today, because this is kind of the backbone of how to simplify your radical expressions here. Okay, so I want to take some time and talk about these. So when you go ahead and you look at a radical, we can undo that radical with an exponent that has a value that's the same as the index, right? So you can look at that here. As long as the root has the same index as the exponent you raised to, then those are going to basically undo each other and leave you with that base number of a that is inside here. You guys can see that in both of these. But here's the thing. If that index number is even, we're going to have to be a little bit more careful, because of negative times a negative makes a positive. That is an even number of negatives, right? When I just recited that, that was 2 negatives that make a positive, and that's an even number. It would be the same way as if you multiplied 4 negatives together or 6 negatives together. These all make a positive because that's an even number of negatives. So for that reason, one of the things you're going to have to kind of pay attention to especially is if that index number is even, we do need to include a set of absolute value bars to just make sure that we represent that our result ends up being positive instead of negative in that case. It turns out that if that n number is odd, you don't necessarily need to worry about that. You don't need the absolute value bars at all. So again, just something that when we move on to simplifying radicals, that's something that we're paying attention to. And then this very last property here basically tells us how to translate between the radical way of writing this idea and the exponent way of writing this idea. And so the main thing that kind of point out here is that the index of the root, when you write it in the radical way, is always going to be the bottom of the fraction in your exponent when you write it the exponent way, okay? And then pretty here that underneath the radical, we are going to take an exponent of m, and that's going to turn out to be the number that's on top of your exponent way of saying it. And that might be something that we use to simplify some of these radicals here in a moment. How do you know when your radical is simplified? These are just a couple of really good informal little guidelines. This second one especially is going to be something we're going to discuss in the next video after this one, rationalizing denominators. But as long as you make sure that you follow the process that we're about to demonstrate here, you're always going to end up with a simplified radical. And so I want to go ahead and take you through that here, okay? Ignore the numbering of each one of these examples, by the way. We just took a screenshot from a different worksheet. So we're going to start with number 16, which I know is kind of weird, but here's the deal, right? So again, what we're looking for is that property number 5 to kick in. We're looking for the index of our root to be the exact same as the exponent we raised to in our radicand. If that's the case, then we could just go ahead and say that those will undo each other, and we're going to be left with what was being raised to the power of 4 underneath that radical, okay? But remember that property 5 says that we need to be a little extra careful here, because if the index is an even number, then we need to include our result in a set of absolute value bars, again, because a negative times a negative makes a positive, and really to extend that, an even number of negatives multiplied all out will always make a positive. So we need to make sure that our final result is positive by including a set of absolute value bars. All right? This next example here is where we are going to be a little bit more meticulous in what we're doing, okay? Because the index of our root here is a 3. And so one thing that's going to really help us out when we do this problem is going off to the side and writing a complete list of all of our perfect cube numbers. Now, if you're in class, that is something that I've already given to you on a half sheet. If you're one of my virtual students, that's something that you can go ahead and find in the folder for this this lesson right here on Schoology. But for right now, for purposes of this video, I'll just go ahead and recreate the list. So we want 1 squared, we want 2, or sorry, I said squared, I meant cubed. 1 cubed, 2 cubed, 3 cubed, etc., 4 cubed even, and that's going to be enough for our purposes here. So 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is going to give us 64, and then the list keeps going in that fashion. What we're looking for is we're going to look underneath the root and notice that the first thing that we have to deal with is the number 8. What we're going to do is we're going to try to rewrite that 8 as something to the power of 3. Okay, and here that's an easier example to do because 8 shows up in our list of perfect cubes, and so we know that it's just the number 2 that's going to be written there. Okay, so we can rewrite 8 as 2 cubed here. And the reason that we might want to do that is because we can think about this 2 as having the enough money to leave. That's something that we've talked about in class, is if your index number is 3, we want exponents of 3, and whatever has an exponent of 3 is going to have enough quote-unquote money to leave the root, okay? And so that's kind of a little informal way of explaining that idea, but it works, right? So that's us dealing with the 8, and now let's go ahead and deal with this z term here, which it says z to the 6th. Remember our goal here. We want to be able to write this so that it has some exponent of 3, okay? So if you kind of think about our video from last time, the P.2 Day 1 video, we talked about exponents. And in that video, we talked about one of the properties of exponents being that if you have power to power, you multiply those exponents. Well, here we kind of have to think a little bit backwards because our exponent here is a 6. And if we want to write it so that it has an exponent of 3, then what we should do is go ahead and write this as y squared to the power of 3. And again, we write it that way because if it's power to power, we would multiply those exponents and get that 6 back that we started with. And so again, here, the reason that we would want to write it that way is because we have just written something to the power of 3, which means that whatever this was, we now have the correct money to leave, right? And again, it's a little bit informal to say money here, but you get the idea. It's kind of a cost to exit the radical symbol there, okay? And you notice that I circled all the things that have an exponent of 3, so that way at the end of my problem I can go back and look at all the things that I circled and then write those outside the root. So here that's going to be a factor of 2 and a factor of y squared, and nothing else is going to be left over inside of that root. And so to finish off the problem, we just have to remind ourselves that if the index is even, we have to include those absolute value bars. If the index is odd, we can leave them off. Here our index is a 3, and that is a odd number, so we don't need the absolute value bars at all. We'll just go ahead and write our result there as 2y squared. Let's get some more practice with that. Again, sticking with the cubes, so we're going to keep our list of perfect cubes in the screen here to reference. But now we're going to go ahead and just do what we did in the last example. We're going to take this part by part. We're going to break up some of the things that show up, and we're going to be breaking them up in terms of a perfect cube times maybe some leftover parts. So if you look at 24, you look at your list of perfect cubes, I think the largest number in this list that's going to go into a 24 is, of course, 8. And that is something that we can write as 2 cubed. So 24 we could write as 8 times 3, of course. And then that 8 we can further write as 2 cubed times 3. And again, we would want to write it that way because the index of our root is a 3, and so we can see here that 2 has enough money to leave the root, and so we'll go ahead and circle that 2. That poor number 3 there does not have enough money to leave the root, so that's going to have to stay underneath the radical symbol whenever we write our final solution here at the very end of the problem. Okay? Moving right along, we have an x term here. X does not look like it has enough money to leave the root, unfortunately. It does not have an exponent of 3 on it, so we're going to go ahead and leave that under the radical whenever we write our final result. Moving on to the y's, it looks like y does have enough money to leave the root because it does have an exponent of 3, and that matches the index of our root there, so we'll go ahead and write that. And then finally, let's take a look at that z term. It's z to the 4th, and so we will rewrite this as something to the power of 3 times what remains, right? So I might rewrite this as z to the 3rd times z. Remember from Friday, if you multiply like bases of z, you would add those exponents and we would get our 4 back. Okay? Well, it looks like here that z is going to have enough money to leave the root, so I'm going to go ahead and circle that z right there. And then that other z right there without the exponent of 3, that does not have enough money to leave the root, so we're going to go ahead and leave that under the root whenever we write our final answer. Okay, so now that I've gone through every single one of my terms, I'm just going to go through all the ones that I circled and write those outside the root, and then everything that was not circled, I'm going to have to leave under the root. Okay, so all the ones that I circled here, that is going to be 2, y, and z. And then everything else is going to have to stay under the root, so I'm going to go ahead and write another copy of the cube root, and then write what we had left over there. Well, that was going to be a copy of 3, and then a copy of x, and then a copy of z. So 3xz, unfortunately, is going to have to stay under the root there. And before we finish up the problem, we'll just take a look at that index and notice that that is an odd number, which means we do not need absolute value bars, and we're just going to go ahead and call this our result right there. Moving on to the next one, we have 4 as our index, okay? And so instead of looking at your list of perfect cubes, we will now want to take a look at your list of perfect fourths, okay? So we'll just write this list informally off to the side here. So 1 to the power of 4, that's going to be 1. 2 to the power of 4, that's going to give us 16. 3 to the power of 4, that's going to give us 81, etc., 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 okay? Check that half-sheet list to get your complete list of all the ones to the 4th power, but here in the video, this is enough for us. So let's go ahead and take this part by part. We're going to start with the 48 there, and we're going to look at our list of perfect fourths and ask ourselves, what is the largest one that goes into a 48? I think pretty clearly here that's going to be 16. We could break up a 48 as a 16 times 3, which means I can further break up 16 as 2 to the 4th, and poor little 3 does not have enough money to leave the root. But the 2 does, so we'll go ahead and make a note of that and circle that 2 and signify to us later that we're going to have to include that in the part that comes outside the root. Okay? Moving on to the next example term, we have x squared. It does not look like that has enough money to leave the root, and so that's going to have to end up in our under the root in our final example, or final answer, I should say. Moving right along here, we have y to the 40th power. Goodness, okay? Well, again, our strategy here is going to be, we're going to rewrite this so that it has something to the power of 4. Because if it has the power of 4, then that means it's going to have enough money to leave the root since that matches the index. So how can we rewrite that exponent of 40 as something to the power of 4? Well, again, we're thinking power to power. We're thinking back from that video from P.2 day 1, and we might notice here that that would have to be y to the 10th because that's power to power. 10 times 4 would make our 40 back. And so y to the 10th power would be something that we would want to write outside of our root in our very final answer. And so finally, we'll end up here with this z to the 5th term, and we'll break that up into z to the 4th times z. And then we see here that this copy of z has the requisite number of dollars to leave the root. Again, a little bit silly and informal to refer to it as dollars necessarily, but it works, right? So I'm just going to erase this list over here just for the time being, just so I have enough room to write. Everything that was circled goes outside the root, so we're going to say 2y to the 10th z. That is everything that had enough money to leave the root. And then everything else is going to have to stay underneath the radical symbol. So we'll say fourth root, 3 was left over. X squared was left over, so x squared. None of the y's were left over, but we did have a z left over, so we'll go ahead and write that z down as underneath our radical symbol, okay? Before we finish up, we're just going to ask ourselves if that index was even or odd. Here that is going to be a 4, and that is an even number, so we're going to include just the part that left the radical in absolute value bars, okay? So again, if the index was odd, we wouldn't have to worry about that step. But because it's even, we do absolutely have to worry about that step, okay? And then a lot of these go very, very similarly to how we said. So the last example that I want to do in this video is just one like number 22, where we're multiplying 2 radicals together. And we can always multiply 2 radicals together as long as these indices are the same. And here we see that they are. They're definitely both 3. So we have the green light to go ahead and continue here. The way I would go ahead and continue is by writing everything under one big cube root, and just look at this as multiplying my 2 radicands together. And we're going to do that part by part. So we've got 12 times 6. If you multiply those out, I believe that's going to give you 72. Let's multiply our x portions together. So that's going to be x squared times x. Those are multiplying like bases, so we would add those exponents. So 2 plus 1, that of course is going to make 3. And then finally, for our y terms, it's going to be y to the 3rd times y. And so adding those exponents again, that would simply be y to the 4th power, okay? So maybe rewriting that root so that we fit a little bit nicely there. And again, this is just going to now be the same old game of what has enough money to leave the root, okay? So our index here is 3, so we're going to look at our perfect cube numbers here. So that's going to be 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, and so on and so forth. And really, we only need to continue the list until we get up to the number that we're trying to meet, which in this case is just going to be, for us, a 72. Okay, so we're safe with this list of numbers right here. We're trying to figure out what is the largest one of these numbers in our list of perfect cubes that goes into 72, and I think here that is just going to simply be the number 8. So if we change this to 8 times 9, then we can go ahead and rewrite that 8 as 2 to the 3rd power. We could write that 9 as simply just 9, okay? And writing it that way, we can now see that 2 has enough money to leave the root, so we'll circle that 2. 9, unfortunately, does not have enough money to leave that root, so we're going to leave that be, and we're going to move on to our next term, which is our x, okay? And x, I think pretty straightforward here, does have enough money to leave the root because of that exponent of 3, and so we're going to go ahead and circle that copy of x to right outside of our root here in our next step. And then finally, that factor of 4, or sorry, not 4, y at the end has 4 copies of it, right? So if we go ahead and rewrite that as simply y to the 3rd times y, then we will see here that this y has enough money to leave the root, and the other one does not, okay? And so when we write our final answer here, I'm going to go ahead and erase my list of perfect cubes here just so I can go ahead and write my final answer. All the things that are circled can leave the root, so for us, that's going to be 2xy. And then everything else that was not circled left over is going to have to stay underneath the cube root. So for us, that is a 9 and a y, and that will finish that up. Okay, so very, very simple to simplify radicals if you are familiar with the process. And so after going through those couple of examples here, I think that is pretty good for one video. So if you guys have any additional questions over this stuff at all, please feel free to let me know. But that's all I have for this one. Thank you very much for your attention, and I'll speak to you in the next one.